In this video here, what we'd like to look at is an LC circuit. And what we mean by LC is a circuit that has an inductor and a capacitor in it. The last time we sort of looked at combinations of electrical elements and circuits, they were RC circuits, where we had resistors and capacitors in a circuit. Well, now we'll look at LC circuits. Okay, so the LC circuit the idea starts with this. Suppose you had a capacitor that was fully charged by some battery or some other means here. And what you did when it's fully charged is you just immediately connected it across an inductor like this. So the question is, what will happen? Well, what will start to happen is, of course, the inductor has this weird property because it's in a coil that wants to resist all current changes, but of course it is just a continuous piece of wire. So what will happen is these positive charges are going to start to flow around like this. There'll be a current like this. And yes, as the current starts to flow into the inductor will initially resist these changes in current, but it will eventually lose because it's the capacitor here that has all the energy. So it will initially resist, but it can't hold off forever. So what will eventually happen is there's going to be a big magnetic field in the inductor here. That's sort of in the final sense of what's going to happen. And maybe I shouldn't draw it all in one figure like this, because by the time that magnetic field starts to build up like that, let me draw just a few different varieties of this here. The charge on the capacitor, of course, becomes less and less as this happens, because the capacitor is losing its charge. So we'll draw some fewer amounts of charge on there, and what we'll draw there is maybe the B field getting a little larger like this. It won't quite be as large as that yet. And then what happens, maybe in a little bit more time goes by, you sort of leave the two connected like this, you'll have a system that looks like this, where the capacitor is completely empty because it's used up all of its charge, and the inductor is sitting here with this huge magnetic field in it that looks like this. So this is sort of the sequence that will happen here. And I think to make it a little more complete, what I'll do is I'll just sort of remove that one there. Now you watched in context when I drew that magnetic field in. I'll just sort of keep the initial state like this here and just say, well, what happens is the fully charged capacitor, the charge starts to flow off of it. The current does find this inductor sitting here, and the inductor goes through its properties that it does. It resists current change, but eventually loses. So what starts to happen is the magnetic field inside the inductor starts to build up. This is the B field right here, at the expense of the charge on the capacitor, because of course the capacitor is giving up its energy and it's going into the inductor. And eventually what happens here is the capacitor will be completely empty, and there'll be this huge magnetic field sitting in the inductor. So the question is, well, what happens now? Well, what happens now is the consequences of the inductors gets kind of interesting, because what happens now is that the inductor sits here with this huge magnetic field and sort of looks back at the capacitor and go, hey, are you still going to give me any of your energy? And the capacitor is going to go, no, I don't have any more left. My plates are empty. So it's almost like you're pulling the rug out of the poor inductor. You've given it this big magnetic field, but you haven't given it any way of sustaining that magnetic field because the capacitor is now empty. So what the inductor is going to do, or what this field is going to do, this field here is going to start to decrease because there's nothing to sustain it anymore. But that's a changing magnetic field inside the inductor. Lenz's law is going to kick in and go, wait a minute, we have this big magnetic field pointing down. In other words, and we'd like to keep this magnetic field, and to oppose this thing starting to shrink like this, we're going to induce a B field like this here. But if you're an inductor and you wanted to induce a B field in the same direction as a magnetic field that exists there, as the inductor, you're going to have to induce a current in yourself in the same direction as that original current. So the original current that actually came in from the inductor produced this downwards magnetic field. So if you want to maintain a downwards magnetic field, you better maintain that current as it used to come in from the capacitor. And if you do that, what will happen here is you need to maintain this type of original current right here. So in other words, in all these figures here, as the capacitor discharges, the current is always in the direction as drawn by these arrows here. Now, if you're this inductor stuck with this big magnetic field here, but the capacitor is all out of charge, and you want to maintain this field, you better start inducing a current which is in that same direction. It doesn't matter where I draw this red arrow, the whole thing's a big series circuit here, but it looks something like this. But if the current is in this direction now, and suddenly the current goes up here, the induced current, this is the induced current for sure, this induced current hits that inductor, you're going to start depositing positive charges on that plate of the capacitor. And these positive charges, if there's positive charges on one plate, negatives will start to be on the other one like that. And this will happen for a little while here. And I'll redraw the circuit even a bit further in time here. And this is exactly what we're trying to get after, these time dynamics here. What happens, something like this, is eventually what's going to happen, I'll draw two more of these just to sort of get it going here. There's the inductor and the capacitor here. Eventually what's going to happen is the inductor will lose. It always does. So it's going to try to maintain this big blue magnetic field, but it cannot. So eventually this big blue magnetic field will start to get smaller. In fact, it might get to be the size of this one over here, some intermediate stage of that capacitor discharge. And you'll start to get smaller, But of course, at the expense of getting smaller like that, the capacitor here starts to get more charge on it like that. So maybe there was this amount of charge before, well now maybe there's this charge, but that field's getting smaller. And now what happens, we'll sort of draw this as the last cycle right here. You go over here, here's that capacitor sitting here, here's the inductor like that, and what you get here is the magnetic field in the inductor will be completely gone. The inductor is not able to magically sustain a magnetic field without some other power supply, but the inductor will be completely devoid of its magnetic field. The B field will be zero. I have nothing to draw on here. Now what you have is you have a capacitor which is fully charged up again. You look at it very carefully and go, aha, well, I'm back to the very first drawing here of this capacitor that's fully charged up. Well, no, not quite. You are left with a capacitor that's fully charged, but notice the orientation of the charges. The bottom plate's positive now, and the top one's negative after all this has gone by. And initially, we had the top plate positive and the bottom plate negative. So that's sort of the situation. The charge on the capacitors has been reversed. So we'll just talk through this now. But guess what happens now? You have a fully charged capacitor and an inductor just sitting there with no magnetic field in. Well, like we did before, this positive charge is going to start flowing this way. And all the same stuff is going to happen again with the inductor is going to go through trying to stop that change of magnetic field and current that you have sort of trying to oppose on like this. But when the capacitor is empty, or as the capacitor empties, a magnetic field is going to start growing in the inductor just like it did before. But look, in the opposite direction. It's not down anymore like it was up there. It's going to be up here like this. And so what will eventually happen is the capacitor will become fully discharged. The inductor will be left with a huge magnetic field in it like that, and the cycle will just start to repeat itself. So what this whole cycle is here, the fact that the charge on the capacitor constantly sloshes back and forth between this polarity and that polarity and this polarity and that polarity, what you've made here is an oscillator like that. So the system here is called an LC oscillator. Now what we're assuming here is that all the resistances in the circuit are zero. In other words, they're perfect wires, perfect capacitors, perfect inductors, and that sort of thing. If you have a system like this here, if say you looked at the voltage, so you put some sort of meter or an oscilloscope or something like this right here across the inductor to monitor the voltage on this thing, you will not get a straight number that doesn't change. In fact, you'll get a number that maybe was initially zero and just starts going up and down like this. So if you created, this is a voltage here, this is time here, you created an oscillation in this voltage here, and this has very huge concepts for us here, because what will happen is that you can choose values of these resistors and capacitors so that this oscillation here can be comparatively fast. And by fast I mean maybe 1 million cycles per second. So this is nothing like the 2,000 hertz sound wave that you did before. This is like a megahertz here, 1 megahertz or something like that. And at these frequencies here, when you have electrons sloshing around in wires like that, of this frequency here, you start getting electromagnetic radiation coming off. And so there's that term right there that we sort of started on the video that we just introduced the magnetic field. Here's that first term here. You get electromagnetic radiation coming out. And that's just an easy way of saying you built yourself a radio transmitter. So if you tune this oscillation to say overlap with the FM band of the radio, you'll hear this oscillation going. Maybe it's a series of clicks or some other background noise or something. But that's the nature of the game here. That's what happens when you dump a fully charged capacitor into an inductor. If the system is perfect, you will get this LC oscillation happening because of the charge sloshing out of the capacitor into the inductor, and then out of the inductor back into the capacitor, but with the opposite polarity. The system in a perfect world would go on forever. Now, of course, real circuits actually have real resistances and things like that, and there's losses, and even the electromagnetic radiation traveling around steals energy out of the system. So in principle, or in practice rather, the oscillation actually looks like this. But it isn't that hard to do in an electronics laboratory with an oscilloscope here to sort of see at least a few of these waves right here, but of course they're exponentially damped. This will be e to the minus a constant times t here as the energy is lost right here due to radiation. So if you want to sustain a thing like build yourself a radio station or sort of have the oscillation continue, you're going to have to find a way of here of injecting energy into it to keep the oscillation going. And the easiest way I can think of it like that is with a transistor. This is one of the first and early uses of transistors and radios and things that people discovered, that you do have these LC oscillations, and if you want to keep injecting energy into them, a transistor can do that for you. And so if you sort of go to Wikipedia or something and look up Transistor Lc Oscillator, if you're lucky, you'll find someone who will present a circuit that only involves just one transistor. Just a very beautifully simple circuit. You'll see the capacitor, you'll see the resistor, you'll see the battery supply, you'll see this one transistor in there, and when the thing is turned on, it'll oscillate forever and ever and ever, at least until the battery goes dead. And it's a way of making sort of like a radio tone transmitter for a radio. But anyway, that's the LC circuit. The important takeaway is that logic here, again, about how the charge leaves the capacitor, goes into the inductor, from the inductor back in the capacitor, and hopefully you can sort of reproduce that logic.